All right, well, thanks for the invitation. As was mentioned, what I'll be talking about is this very long title. I think the best way to read this title is kind of actually backwards. Well, I'm interested in quantum field theory. I'm interested in quantum gravity. I'll explain what I mean by quantum gravity when we get to it. And I'm particularly interested in scattering theory, as I guess is part of the prehistory of how even QFT was developed. And in particular, when you encounter scattering theory, it has been well known for some time, you run into these infrared issues. Okay, so the basic point is, what I'll describe is what these infrared issues are, where they arise, and one reason I think it's appropriate to give this talk to this crowd is because a lot of the issues that arise can be seen just from the classical structure of the theory alone. Okay, and so that's the idea. Everything that I'll describe today will mostly be contained in this paper that I highlighted here, but there's a couple in preparation that I'll maybe get to at the end if we have time. Okay, so this is a primer on just scattering theory in general, and as well, I don't know, most of you aren't, or maybe aren't quantum people or anything like that, so these are just, you should view these as just facts maybe about scattering theory if you're not familiar with them, but conventional scattering theory with massive particles has been well understood. So this goes back to work by LSZ and Hagen Ruel, who really studied these how to define scattering theory when one has massive particles. That's not the subject of my talk, but one runs really into serious issues in defining scattering theory for massless particles. Okay, I'm particularly thinking of when the massless particles are coupled to massive particles or undergo suitable self-interactions like will occur in gravity. Okay, and these run the serious issues that I'm referring to here are these IR divergences that I alluded to in my title slide. And what we'll see is that these IR divergences are related to this classical gravitational, or this classical effect, which I'll explain is called the memory effect. Okay, so, well, I just said that there are serious issues in scattering theory, but if you read a QFT textbook, they go beyond massive particles, and the textbook continues on. Well, the reason for that is because people have figured out ways of not defining the scattering theory and still obtaining some reasonable things. And as you'll see, okay, there we go. In particular, this is going to be a problem, I think, but we'll keep going on. So what one finds is that, what they define are these so-called inclusive cross-sections. I'll explain what those are later in this talk, but the basic point is that the standard scattering theory, what's called the S-matrix, is undefined when one has massless particles. So without a scattering theory, this is not going to be good, I think. Let me see if I can fix this. Must be due to the connection. Yeah. Okay. Well, the whole point of the talk is to not use S matrices anymore. So I guess that's a good thing. Okay. So the point is, if the standard scattering theory is undefined, what you end up, one basically cannot address low frequency observables. Yeah. Let me just try disconnecting and connecting again. This is all being recorded, right?
It is.
Okay, good. Let me try, I have another port. I can try this other port and see if it's better. Sorry about this. Okay. Full screen. Okay. So the basic point, and as we'll see explicitly in this talk, there are lots of questions you could ask about the scattering theory which cannot be addressed in this framework, which in particular, if you want to study low frequency effects of scattering theory, these cannot be addressed within this particular framework. And that's because of the fact that you're basically, the standard approach, these so-called inclusive cross-sections, tells you to truncate the state at very low frequencies and pretend you're working with a state that doesn't have any of these IR issues. Okay, so we'll see this explicitly. So that's the basic point. This approach was pioneered in the 30s by Bloch and Nordsick and refined in the 60s by Weinberg or whatever. And the basic idea is that you can still make predictions for what people see in the LHC or something, but the fundamental statement, which is that, is the standard scattering theory well defined? Can I ask any question I want about the quantum field theory? The answer is no, you cannot, right, within this framework. Okay, so that seems like a really bad scenario to have quantum field theory be standing upon, but remarkably, what ended up happening was in the 70s, Faddeev and Kulish, very remarkably, did provide an infrared finite formulation of the scattering theory. This was not in the framework of Bloch and Nordsick or Weinberg or any of these other people. They really proposed a totally new formulation of the scattering theory, which was infrared finite. So what the point of this talk is, I will explain the origin of these divergences, why what Faddeev and Kulish did was in some sense inspired, but what ultimately we'll ask the final question, which is, does this construction or any construction actually generalize to more general theories? And in particular, does there exist a well-defined S-matrix in just quite generally? Okay, so does everyone understand where we're going and what I want to do? In particular, I'm interested in quantum gravity. Okay, so now so a lot of the infrared properties of the theory can be understood just at the classical level. So the first half of my talk is just going to be about classical, waves. In particular, there's a gravitational, gravitational so-called memory effect, which I'll highlight here. So what is the gravitational memory effect? Well, if you have a ring of test masses, and I allow a burst of gravitational wave to pass through this screen, well, we've hopefully all seen, the pictures where it oscillates back and forth in this kind of quadrupolar fashion. But the memory effect is the observation that if the gravitational wave passes by, the test particles may be permanently displaced relative to their original positions. Okay? So this is an instance of the gravitational memory effect, and you can just quantify this effect by just integrating the geodesic deviation equation regarding the displacement between these particles. If I'm at leading order in R is the distance away from the source of the gravitational waves. In this particular case, I'm thinking of it as a null coordinate. The change in the displacement at leading order in 1 over R of some neighboring pair of geodesics is related to the initial displacement, that's this C naught, by this delta here. Okay? And if the delta, this tensor, is not 0, then we have a non-zero gravitational memory effect. Okay? And I said there's a gravitational version of the story. There's also an electromagnetic version. You don't need a whole array of test masses. You just need a single charged particle. And if I have this charged particle that's initially at rest in my lab, let's say, I allow a burst of electromagnetic radiation to pass by. If this particle gets a net momentum kick due to the passage of this burst of electromagnetic radiation, this is an instance of the electromagnetic memory effect. And this change in the momentum at leading order in the distance from the source of the radiation is what encodes this electromagnetic memory. Okay, so it's a very simple thing in terms of the, what you would observe in the lab. And in particular, LIGO is hoping to observe this, within the next, when Lisa turns on, whatever that is. Okay, good. So I'm telling you that I'm interested in bursts of radiation. So in particular, what kinds of radiation am I interested in? Well, I'm interested in radiation arising from scattering scenarios. So what I've depicted here is the kind of scattering scenario that I'm interested in. Well, this could be, the scattering of some charged particles or the merger of, maybe some black holes in my space-time. I'm considering an asymptotically flat space-time, and the radiation, if it's, radiation that I'm, well, by definition interested in, I'm interested in radiation that's dying off suitably rapidly near spatial infinity, and all the way as retarded time goes to the future here. I can tell you the particular decay that we need, but it'll be clear from the integrals I'll write down what decay is necessary for these situations that I want to consider. Okay, so where u here is the retarded time along these along scry, and theta here will be my angular coordinates on these very large spheres. Okay, and so what is the memory? Well, the electromagnetic memory, I said, was the net momentum kick of a test body, of a test charge. Well, by Lorentz force, that means that it's the integral of the electric field over all time, right? Because it's the net momentum kick. So the memory is related to the total integral of the electric field over, at leading order. This is at leading order in 1 over r, where r is the coordinate that goes null in this direction. So the memory is this total integral of the electric field. If I write that in terms of the vector potential, so if I write the electric field in terms of the derivative, the time derivative of the vector potential, then what I mean is that if you're looking at the waveform of the vector potential as a function of retarded time, well, it'll maybe oscillating due to the fact that I have some non-trivial stuff happening in the bulk or whatever, but at late times, if the radiation has memory, that means that the change in the vector potential between early and late times is not 0. Okay? So that's what these formulas say. So what is the gravitational version of this story? Well, I've copied and pasted the same picture to highlight how similar the scenario is. So now the radiation is encoded in the news tensor, which formally is the time derivative of the metric at scry, and the memory is the total integral of this news. Okay, so that means that if I was looking at my LIGO detector and watching the displacements of my particle, well, that's, LIGO is really measuring the change in the metric at, between successive times, and what they'll end up seeing is a permanent displacement of the metric between early and late times. Okay? So this permanent change in the metric between early and late times is a manifestation, again, of the memory effect. Okay, is anyone confused about how memory looks like in terms of so-called signal? Yes, but that's subleading order. And there is a net momentum kick, but it would be at 1 over r squared. Okay, so if I was just giving a talk about memory and wanted you guys to go detect it, I would end the talk right here. But I'm actually interested in slightly deeper properties of this thing, and in particular, there's a really nice reformulation of the memory effect in terms of these charges and fluxes. And that's what I'll describe on this slide. This will be basically integral to understanding the problem in the quantum theory, so I'm going to go through this slowly. So what I can do is if I pick a cut of scry, I can look at the radial component of the electric field. This 2 means the 1 over r squared part of this radial component. And I can, if lambda was a constant, this would be the total electric charge on this cut. Okay? But now I'm going to let lambda be an arbitrary function of angles. You just can't stop me. So I will do this. I want to consider this charge now as an arbitrary, eating now an arbitrary function of angles. Okay, and the reason why that's a nice thing to do is because you can rewrite this memory in terms of the difference of charges. So if I take this charge, so I take the memory, I smear it in. This derivative is a derivative on the sphere. So if I take this memory and I smear it in with this arbitrary function of angles, you can rewrite this by Maxwell's equations in terms of the difference of these charges. So what am I doing here? I'm what I mean by this symbol is that I take this charge and I take this cut and I take it all the way to the future. That's what this guy is. If I take this charge here and I take it all the way to the past, that's what that one is. If I take their difference and then I also compute the total outgoing flux of any massless charge current that gets out the scry, that, by Maxwell's equations, is equivalent to calculating the memory, smeared with that lambda, but then I can do it for all, any lambdas that I want. Okay? So you maybe aren't too surprised that I can also do this for any incoming data that I have. So if I have any incoming memory, which is any electromagnetic radiation with memory that is defined on scry minus, I can rewrite that also in terms of the difference of charges in this limiting in this manner, plus any incoming massless charge current that goes in through scry. Okay. Note, if lambda was a constant, the left-hand side vanishes, and this is just the statement of global charge conservation. Okay. So why I said I was interested in scattering theory, and I'm telling you this story. Why am I interested in this reformulation? Well, these charges, and I'll have a whole slide on why and in what situations this has been proven, but these charges have been shown, and the operative word is shown, which I'll explain in a second, have been shown to match in the following way. This is an antipodal matching. So if I take this cut all the way to I naught, this charge matches to the similar charge that I take from the future in this antipodal manner. So lambda tilde is basically an antipodal map on the sphere. Okay? So this is, well, I'll again explain the status of this particular story in a slide or so, but let me also tell you the gravitational version of this. So these charges here, so now the data here, the basic point is that the data here determines some charges coming in from the past. These charges have been argued to match to the future, and this now gives a non-trivial constraint between incoming data and outgoing data. Just like global charge conservation gives you a non-trivial constraint between, a simple one, but this is now for every function of angle. Okay? So what's the gravitational story? Well, again, I've basically repeated the same symbols, but added extra indices. So the charge now, in a stationary era, is very simply related. Is just the integral of this Weyl tensor component. So this would be psi2 roughly at 1 over r cubed at large distances. If you're not familiar with that, if f was a constant, this would be the total mass on a cut of scry. If f was an L equals 1 spherical harmonic, it'd be the momentum. Now I'm going to let f be an arbitrary function of angles. Okay? So that's this charge again. Again, I do the same game where I take the limit of these charges to the future and the past, and if I take their difference, and now what I'm going to integrate is the total flux of energy, the Bondi nu squared, integrated against that function of angles. That right-hand side gives me, by Einstein's equation, a formula for the outgoing memory. Okay? And while I can do this for the outgoing data, I can again do this for the incoming data, and these charges have been argued to match in exactly the manner that I've been discussing in the electromagnetic case. Okay. So the matching of these charges is something that I will assume in this talk. If they don't work, the scattering theory is much harder to do, so I'll explain the best case scenario for scattering theory as formulated currently is if these charges match. If they don't match, then the statements I will be saying, which is that we need to abandon the current approach, is clear. If they do match, then you have a handle on the problem, and you can possibly do the scattering theory as currently formulated. So what I'll be doing is I'll be assuming this matching just to even get off the ground. We'll see that if you don't assume it, the scattering theory is going to be much harder to do, or basically impossible in the current framework. So, okay, so what is the status of the matching of these charges? Well, these charges have been shown to match when you assume some rigid structure at spatial infinity. In particular, these Ashtekar-Hansen conditions, or a slightly strengthened version of these Ashtekar-Hansen type conditions, or Baig-Schmidt conditions at spatial infinity. This has been work by basically Kartik Prabhu since 2019 and continuing, where they're currently looking at, I think, even doing this in the Friedrich formulation. So why am I hedging as to whether or not, so these are, well, way back in the 70s and the 80s, that was a really nice, you just assume some structure and then you try to prove statements assuming some structure. Well, now that we're in the current century, it would be nice to prove this from, I'm not saying I want to do this, but it would be nice to prove this from, using the Christodoulou-Kleinerman type analysis. Okay, and you could ask, well, why? I mean, the Christodoulou-Kleinerman, we're doing a lot of work. It's a very long book. Why isn't it in there? Well, the Christodoulou-Kleinerman data assumes the metric is exactly Schwarzschild at large distances. And if you run through what these charges are, what you end up getting is, well, this mass is spherically symmetric, and as a result, all these higher harmonic charges are identically zero in their initial data. Okay? So the matching is trivial in their case because all of the charges vanish. What would be really nice is to consider initial data that's slightly weaker than the one that they were considering, in the sense that now I'm going to let this mass be an arbitrary function of angles. And in this sense, this would yield super translation charges that are not zero for your initial data. And then what would be really nice is to prove that these charges really do match when you evolve to the future. And, well, if you have a null infinity, I'm assuming that, and you can then try to match the charges from the past and the future. So this would be really nice to prove. And as I hope I'll explain in this talk, this conservation of at all higher harmonics, this conservation of super translation charge really, well, if I haven't mentioned the BMS group at all, but those who do know, gives you a nice global identification of the BMS group between the past and the future. And as I'll explicitly explain in the talk, places very strong constraints on quantum scattering theory. So this is my motivation slide for anyone who wants to actually please prove this in much more rigor. I should mention, I think Lydia Bieri is currently thinking about stuff in this framework. So if you're interested, I would contact her and see how far she's gotten or something in this idea. But I think well, there's a lot to do. These are just the super translation charges, but matching all of the charges from Scry plus to Scry minus is also an open question. Okay, does anyone have any questions about this slide? Okay, so this is the last classical thing that we'll do in this. And now we'll go to the quantum theory. So, well, and in my talk, well, in the beginning, I mentioned that I'm interested in quantum gravity, and a question you might have is, what do I mean by quantum gravity? Am I picking loop or string or something like that? Well, really, all of the statements I'll be making are, while I said it's about scattering theory, I'll be reformulating the questions in terms of kinematic questions about initial data. And in that framework, I don't really have to specify what the theory is in the bulk. It was pointed out by Ashtekar in the 80s that the radiative degrees of freedom, like this news tensor at Scry, can be exactly quantized. This is roughly because of the fact that gravity is effectively linearizing at Scry to a point where you have a nice symplectic structure on the news data, and you can exactly quantize it irrespective of what the bulk scattering theory is. Okay, so really what I'll be explaining is basically all just kinematic concepts at the moment, because we're really going to be interested in Hilbert spaces and so forth. So the radiative degrees of freedom can be quantized even in the absence of a bulk theory. And so let me explicitly show that to you. So for example, one can construct the standard Fock space of gravitons in the following way. So what is a Fock space? Well, all I mean is that I'm going to construct a Hilbert space of initial data, okay? A Hilbert space where the norm, or there's an inner product, but it's more, well, for this particular discussion, it'll be nicer to just to write the norm. The norm on the metric, these, that I have at Scry, is given by the following expression, where H tilde is the Fourier transform of the metric with respect to retarded time. I'm integrating over positive frequencies and integrating over angles. Okay? And so this is the standard Fock space. So if I was doing perturbative quantum gravity in the bulk, this is what Peskin and Schroeder would tell me to write down as the norm on my on the metric perturbations that I would have. But you can exactly write this norm down at scry in terms of the initial data at scry. Okay, so why is it useful for me to tell you this exact formula? Well, it's not important that you remember all the details, but you just should remember that I'm integrating over frequencies and I have this power of omega there. Because it's immediately clear what's going to happen when I have memory, which is that, well, if I have non-zero memory, that means that the change in the metric between early and late times must be non-zero, which means that if I Fourier transform this at very low frequencies, it's got to look like the Fourier transform of a step function, which diverges like 1 over omega at low frequencies. Okay, if you plug that into the norm, what you'll end up getting is that the norm of the metric in the Hilbert space that you want to quantize in is logarithmically divergent at low frequencies if the memory is not zero. Okay, what does this mean? Well, the standard Fock space that you're supposed to use in scattering theory doesn't contain any states with memory. Okay? And any state with memory will have infinite norm in the usual Fock space. There is, I hope is clear, nothing physically or otherwise wrong with states with memory, and they will unavoidably occur in scattering theory. The infrared divergences that have been, have been around since the 1930s simply arise when you try to pretend that the state that you get from scattering theory belongs in the usual Fock space. And the basic point is that if you want to, so you can put an infrared cutoff on the state and pretend that the state lives in the usual Fock space. Every formula that you use now using this state will depend on the cutoff. And the game of these so-called inclusive cross-sections is to compute some observables that are independent of the cutoff. This is more of an art than a science because it depends on the observable that you're interested in. For example, if you tried to compute the outgoing memory of a quantum state, it will definitely depend on the cutoff. And so basically, this inclusive cross-section approach pioneered by Bloch and Nortzig and Weinberg was basically just find some observables that don't care about the low frequency content of the state and try to compute those. Okay? But if one wants to have a well-defined S-matrix, means all degrees of freedom down to the infrared are kept track of, one needs to just include states with memory into the scattering theory. Okay, is anyone confused about what we need to do? Okay. Okay, so what does a state with memory look like? Well, it's really easy to make one if I have a classical solution with memory. So let's start in the standard Fock space where I have this news, boldface just means operator. So I have a news operator, and I'm just going to shift it by a classical solution. So this is the news operator in the standard Fock space. This has no memory. Now I'm going to just shift it by a classical solution with memory. And now I've constructed an operator with memory. This is a classical solution times the multiple of the identity. For those of you who know, what I've done is I've just made a coherent state with memory. And I've given it memory because I've told you that the integral of this classical solution, the news, is non-zero. It's given by this memory. Okay, so now all of the states, so if I had a state on this, on the standard Fock space, if I do this shift, all of the states now have memory. And they're all going to have this memory delta, the same memory before, because all of the states in the standard Fock space had no memory. I'm going to shift them all by this classical solution with memory, and therefore I'm going to get a new Fock space of all new states with memory delta. That's what this F delta is. And well, the point is that, well, all of these have memory delta, this has memory 0, and what you can, it's straightforward to show is that this Fock representation is unitarily inequivalent as a representation of the algebra, of the news operators to the Fock space with 0 memory. And I did this for one delta, but you can do this for any delta, right? So I could have started with this guy and shifted by a different memory, and I would get another Fock space, F delta prime. And that F delta prime will be also inequivalent to F delta, it'll be inequivalent to F0, and so on and so forth. Okay. So, and all of the states in F delta, in one of these memory Fock spaces, will be eigenstates of the memory operator with this definite eigenvalue, delta. Okay, what I tried to just explain, and please let me know if I need to restate it, is that there are an uncountably infinite number of in and out Fock spaces with different memories. So what do you do? Like, I started with this one Fock space. I shifted all of the states by one memory and got a whole Fock space of memory delta, and I'm just going to keep doing that. And each one of these Fock spaces with different memories are going to be unitarily inequivalent to each other. And they're all going to be labeled by all the possible in and out memories that I could possibly have. As a representation of the algebra, of the news, yeah. Every separable Hilbert space is unitarily equivalent to every other, but I mean as a representation of the news algebra. So does it carry the news operators? And is that clear? Okay, so what do I have? It looks like I've made my problem way worse, right? It looks like I started with one Fock space, and now I've given you an uncountably infinite number of them, okay? And the memory is not conserved, so the standard S-matrix, again, does not exist. If I send in a state with 0 memory, I'm going to get out states with many different possible memories. And I really need to include all of these F deltas into my scattering theory. Go ahead. Yeah. Is there chalk? Yeah. So had you restate the question again so I can? Yeah, so it doesn't necessarily. For example, if this memory, if this field redefinition that I gave you here had 0 memory, then it wouldn't give you an equivalent representation. So yeah, I actually don't know what to write now. But the basic point is that this only will give you an inequivalent representation if the solution has memory. If you try to write this as a unitary map on the Hilbert space, so what you want to do is to write this guy here, this guy, as something that looks like U, and U, right? Something like this, NAB. Okay, so this is a coherent state. This U then would be a coherent state transformation. Okay, and then the basic point is that if you try to write, for example, like this U as a unitary map on the standard Fock space, right, F0, I'm going to write this, but this is not the case. So this U will not be a unitary map on the standard Fock space if the news, this N, A, B, integral du, is not 0. So I've just restated again what I'm saying here, but I've just maybe put the U's around it. So hopefully it's more clear. Yeah?
Isn't it true in general that if you is unitary inequivalent, any state if you go to
you aren't picking a particular choice, but
so isn't it true in general? I mean, if you even forget about memory.
So are you referring to the Stone-von Neumann theorem?
Yeah, because you are taking representation on some Hilbert space.
That's
so
right.
when you take the representation to some Hilbert space, then you are always, you can take other one, and then there is no way, even if there is
No, that's not true. Like, no, for example, I mean, you can explicitly check this for the case where this map corresponds, like, let's say this is 0. I'm not sure exact, because the Stone-von Neumann theorem is a statement about finite dimensional quantum mechanics, so doesn't apply in this case. No, there could be. The statement about the violation of the Stone-von Neumann theorem says that there might be inequivalent representations, but that doesn't mean that dynamically occurs in scattering theory. So for example, if you have massive fields, then if you start with states in the standard Fock space for massive fields and you scatter, it has been argued, well, at least perturbatively, that the out state does lie in the same Fock representation as the in Fock representation. So there do exist inequivalent representations, but that doesn't mean that they dynamically occur as you evolve. Like that you will get an out state that does not lie it lies in such an inequivalent representation. What I'm saying here is that basically whenever you have non-zero memory, dynamically you are kicked out of the in-Hilbert space. Okay? How much time do I have? 20 minutes, okay. Okay, so what sort of Hilbert space? Well, okay, so now we need to include all of these Fock spaces with different memories. It looks like I've made this problem way harder, and in a sense I really have. And so let me say exactly how hard this is. So, well, what sort of Hilbert spaces do we need to include? Well, we need to include sufficiently many of these memory representations together to ensure that the corresponding Hilbert space that I'm now using scatters into itself. Okay? But the fundamental obstacle to this is that the memory is not conserved. So any construction that I do that tries to put together these memory Fock spaces, there's no guarantee that I don't have a, quote, amplitude to scatter out to a different representation. I mean, there's nothing in any sense preferred about any construction that just tries to put these memory Fock spaces together in some naive way. So for example, you could try some crazy thing like an uncountable direct sum over all possible memories. It's, let me not say too much about this, but it's, you can straightforwardly argue that this is not going to even be preserved under scattering. You could try to do something more fancy like a direct integral. The devil here is in this measure, which is this measure is on the space of all memories, which is an infinite dimensional space. So you need to write down an infinite dimensional measure. In the paper, we study even just the class of Gaussian measures, and we find we give strong arguments that there is no Gaussian measure that would give an admissible scattering theory. And in particular, even if you found an in-Hilbert space in which with any choice of measure, you would have to argue that the scattering theory preserves this choice, which is an arbitrary choice. Go ahead. Yes. It commutes with the kinematic data. So the news, the memory commutes with the news. And the scattering is still uncontrolled. So this is largely the reason why, as far as I can tell, why there was very little progress. It was pointed out by Heisenberg, this problem in the 1930s, not in this framework, but it was pointed out. And there's basically been almost no progress until the 70s on this problem, because what do you do with all of these, with all of these different possible states that you could, try to put together? Why does it commute? Let's see. The reason it commutes is because the way the memory is defined as an observable on the data is with respect to these super translations at infinity. So I could go through that argument. It's not a straightforward argument. It's basically, the basic point is that the memory operator is defined. The memory as an observable on phase space is something that generates on the initial data a super translation. And the super translations, What? No, yeah, no, it's fine. Though what it does is the following. EADB. So the map, the memory is associated to the following map on initial data. And this, so if I take a derivative of this, a time derivative of this, f is a function on the sphere, it maps the news into itself. And so it commutes as an observable on phase space, and then when you quantize it, it commutes. Okay. Okay, so the basic point, or the question is, does there exist an in-Hilbert space of states that scatter into themselves? And so in the last 15 minutes or so, well, you know, like any good problem, you know, a lot of people, well, have tried or whatever, and one key idea that was introduced by Faddeev and Kulish in the 70s turns out to be particularly inspired. So let me explain to you what that is. This is not how they would have explained it, but this turns out to be exactly what they did, which is pretty remarkable because they didn't have any of these ideas like memory or charges way back in the 70s. Okay, so the real way of phrasing what they're saying is that they're going to use this conservation of charges at spatial infinity. And therefore, the in-Hilbert space, if you construct an in-Hilbert space of eigenstates of these charges at spatial infinity, you can then argue by this conservation that these in-Hilbert space with this eigenspace, with the eigenvalues, with eigenvalue given by this definite charge Q, will map to the out-Hilbert space with this antipodally reflected eigenvalue. Okay? So the basic idea is to construct an in-Hilbert space, which is an eigenstate, with eigenspace of this charge with this particular eigenvalue. Okay? And these charge eigenstates are states in which the electromagnetic radiation, the memory, is highly correlated with the incoming electron. And these are what people call dressed states. I've really wondered that for a long time, and this is how you think about it. So if you pick a charge at spatial infinity, some definite charge, you know, at spatial infinity, you can construct these dressed states in the following manner. So you fix this charge at spatial infinity, you send in an electron, but don't send in a whole wave packet just yet. Just send in a formal plane wave. We're going to make a wave packet in a second. Send in this formal plane wave, and you can show on the Fock representation of these electrons at past time like infinity, these charges have, or, you know, these plane waves are kind of these, are eigenstates of these charges, and the eigenvalue really just corresponds to the, you know, this radial component of the electric field associated to a classical particle with that momentum. It just turns out to be the case, that it has this definite eigenvalue determined by this charge here. And so what I'm going to do is I'm going to just solve this equation now, where the right-hand side is the fixed charge that I've decided to choose, and the incoming state, the incoming charge of this electron is determined by its incoming momentum of this guy here. So that's the right-hand side. And then I'm going to solve this equation. I mean, so the L equals 0 part or whatever is I have to project out, but then I can solve it for all the other higher harmonics, and I can tell you what the incoming memory is that I have to correlate with this incoming charge at spatial infinity, or the incoming charge at past time like infinity. So the electromagnetic state that I'm going to choose is not going to be any electromagnetic state. It's going to be an electromagnetic state where the memory is exactly fixed by this relation. Okay? So I take this plane wave, I tensor in this electromagnetic state with the memory given by the fact that I want a definite charge at spatial infinity, and then you integrate and you make up a wave packet of this type that I've made here. So this is what people call dressed electrons. And well, I did it for one electron. You can imagine doing it for any number of electrons and doing the same story. And this corresponding Hilbert space is a Hilbert space of what people call these dressed electrons. Okay, so one thing that was pointed out in the 9 years later after Faddeev and Kulish published this idea is that these charges, this radial component of the electric field at large distances is not Lorentz invariant. And so if I try to restrict to a Hilbert space of definite charge, Lorentz boosts can't act on this Hilbert space. It's like trying to define a Hilbert space of definite position. The infinitesimal the momentum operator is not going to be well defined on such a Hilbert space. In the same manner, Lorentz boosts cannot act on this Hilbert space that I've just constructed unless I set all of the charges equal to 0. Okay? So this is a little odd. So angular momentum is undefined in all of these on this Hilbert space unless I set all the charges to 0. That includes the total electric charge. So that means in order for this to work, one has to put basically all of these extra. So if I send in an electron and I dress it in that particular way, I have to send in also a positron, also dressed in exactly the same way as I'm describing here. And the basic point is, that's a little odd, but it was pointed out by these authors that, well, maybe that's okay because whenever you're scattering some electrons over here, you might as well have some dressed positrons behind the moon somewhere, just hiding to set all of these charges equal to 0. And you can't really argue with that. Well, I'm not endorsing any point of view here. I'm just reporting the facts of what happened. And if you take all of these huge grains of salt, then the Hilbert space of charge equals 0 has all of the properties that you might want in a scattering theory. Well, it constitutes states of all finite energy and well-defined angular momentum. It contains all hard scattering processes because all the radiation that I have to dress with can be tuned to arbitrarily low frequencies, and I can put all these charges behind the moon. And it's a separable Hilbert space. Well, and that's, we don't want to work with anything besides that. Okay, so, yes, go ahead.
When you say massive.
No, sorry. Massive meaning the electron is massive. There's a version of this talk. What? Yeah, but you can do this with massless charges too, which I just omitted in this talk. So standard QED. That's right. That's right. So yeah, sorry. We also did massless QED in the paper, which is why I'm delineating the two. And consequently, you can argue, given all of these points or these ideas, that there exists an S-matrix that, defines as a map on this Hilbert space into itself. Okay? So the basic point of one of the points of our paper is to show that this construction absolutely fails in every other theory. And since I'm, running out of time, let me just jump straight to gravity. Okay, so recall in gravity, the charge was given by this expression here, where it's given by the sum of the incoming memory of the state as well as the incoming energy weighted by this function of angles. Okay, so the first problem that you have is that the charges can't be set to 0. I mean, the charges contain the Bondi mass and the form momentum, or the ADM mass and the form momentum. You don't want to set those to 0. There aren't a lot of states with vanishing form momentum. You would only have the vacuum if you tried to set all the charges to 0. Okay, so that already invalidates the construction because I want to have I want Lorentz to act on my Hilbert space. But you could just say, well, what if, you've talked for an hour, I guess, or almost, you talked for an hour, can you just, can we just do anything? Can we just set these charges to not 0 and find a Hilbert space that at least scatters into itself? Okay, so that's, we investigated this as well, and what you can show is that, the situation is much worse than as alluded to in this bullet point. The only eigenstate of this charge for any eigenvalue is the vacuum with vanishing eigenvalue. Okay, so what is, let me give you the intuition here. This is not how we prove it, but this is a much more intuitive, you can do it this way too. You can think about it this way, but the proof is not of this flavor, where the basic point is that the memory and the energy flux are not independent quantities. Okay, so let's try to do the Faddeev-Kulish dressing, where I send in an incoming state with no memory and just incoming energy. Okay? So that's not going to be an eigenstate of this charge with some definite eigenvalue. But then what Faddeev and Kulish would say is, no, just send in a little bit of memory, like some memory, or some little bit of radiation with memory to cancel off the contribution that you're getting from the second term. But that radiation with memory, even no matter how low frequency it is, doesn't have zero energy, and will then contribute more of the second term. And then you could say, well, no, okay, then just add in a little bit more radiation with memory to kill off that piece. And the basic point is that this construction will never converge to anything, to an eigenstate. And the only way to get this to converge is to send in a state with zero energy and zero memory to start with. Okay, so what's the point? Well, I argued or showed you that we need to include all of these Hilbert-Fock representations with memory. That's a really hard thing to do and very difficult, and we investigated many different ways of possibly doing that. There is this other approach based on conservation of charges, and that also fails in every theory besides massive QED. And really what we're trying to point out here is that there does not appear to be any preferred Hilbert space for scattering generally, and in particular in quantum gravity. And do I have like 3 minutes? Okay, and then, so now, I mean, I've been pretty down about scattering theory, I guess, for the past 40 minutes or so. What do you do differently? Well, the point of view that we would take is that just to step back and ask, what are the well-defined objects of the theory? Okay, so the correlation functions of all states are perfectly well-defined. The basic point that we're pointing out is that the states relevant for scattering theory don't all lie in a single Hilbert space representation. Okay? So now there is a point of view that is worth explaining in at least a minute or two, which is, so if you gave me a state as a state in a Hilbert space, I can always express that state as a list of correlation functions. Okay? That's no problem on some algebra. So for example, if I could express a state psi as a list of correlation functions, a 1-point function, 2-point function, and so on and so forth, and that contains just as much content as this symbol. Okay. So conversely, if you give me a list of correlation functions on an algebra satisfying certain rules like commutation relations and positivity, as we heard about a little bit yesterday, one can construct by this GNS construction a Hilbert space where this list of correlation functions is packaged as a vector in a Hilbert space. And therefore, viewing a state as a list of correlation functions or a vector in a Hilbert space are essentially equivalent from this point of view. However, considering states as a list of correlation functions, one is freed from choosing in advance any particular Hilbert space that I want to be considering. And that is the whole point, in my point of view, of solving this problem. So given a set of correlation functions on some in algebra, you could just ask, what is the expected value of any out observable in that state? Well, what you can do is you can just take, you can use the Heisenberg equations of motion to take this out algebra element and map it to the in algebra and compute any correlation function of any out algebra element you want in terms of, things that in terms of the in correlation functions that you sent in. And in this manner, you can completely formulate scattering theory in a manner that is manifestly IR-finite. In this whole framework of defining what I mean by an in-correlation function as a list of in state as a list of correlation functions, and then evolving those correlation functions, or in this manner, one does not need to presuppose what the out Hilbert space is, or or anything of that sort, and therefore is manifestly IR-finite. And that's the game. I mean, you just should formulate scattering theory without ever presupposing whatever the out Hilbert space is, and such a construction would be manifestly IR-finite. And so this in this framework, we spell it out in a lot more detail in a paper that's coming up for a massive scalar field coupled to massless. The reason we just do scalar is that we can ignore any gauge issues that we just didn't want to deal with in this particular, just to explain how this whole setup would work. But what you can calculate is, you can send in any in-state you want. It doesn't have to be dressed. It doesn't have to do anything in particular. And you just evolve them, and you can calculate the out-correlation functions of the memory, the charges, of whatever, and it's all manifestly IR-finite because I never said the word Hilbert space. Okay, and with that, I'll end my talk.